Quite frankly, I'm a little skeptical that this ever appeared on a Harvard entrance exam, but it is a beautiful little problem, so let's walk through it. How would we solve this equation? X plus 1 times x plus 3 times x plus 5 times x plus 7 equals 9. Let's start by saying this. This equation is in a particular form. It's in what's called factored form. And if it simply said x plus 1 times x plus 3 times x plus 5, etc., equals 0, it would be extremely simple to solve. We would use something called the zero product property, which basically tells us the only way to get a result of 0 if we're multiplying a bunch of stuff together is if at least one of the stuffs we're multiplying together is itself 0. Meaning in this case that the only way the equation could be solved is if x was something like -1, because -1 plus 1 is equal to 0, and then it doesn't even matter what happens with the other sets of parentheses, because anything times 0 is 0. So we would also have solutions at -3, since -3 plus 3 is equal to 0, -5, and of course -7. Unfortunately, if we don't have that 0 on the other side, factored form does not help us. If anything, it's going to make our job more complicated because first we would have to multiply all this stuff on the left-hand side out, and multiplying 4 different binomials is not the easiest process in the world, usually. Then we would have to subtract 9 to get a 0 on that right-hand side, and then finally refactor whatever was left over and solve it from there. This is, of course, our Harvard entrance exam, so we can't spend that much time on a single problem. What should we do instead to be a little clever? You might notice, 1, 3, 5, 7, it's interesting that those are increasing at such regular intervals. Let's actually try to take advantage of that by doing some clever substitution. I'm going to pick a number right in the middle, and I'm going to say, let's have a different variable, u, stand for x plus 4. And we're going to rewrite all these expressions now in terms of u. Something like x plus 1, for example, would now be the same thing as u minus 3, because of course if we subtracted 3 from 4, we would get 1, and so u minus 3 is the same as x plus 1. For that matter, x plus 3 can now be rewritten as u minus 1, because again, by the same logic, if we subtracted 1 from x plus 4, that would give us x plus 3. And of course, if we're going to subtract on one side, we need to subtract on the other side of our equation as well. So that's how we know x plus 3 is the same thing as u minus 1. As we keep doing this all the way across, x plus 5 would be the same thing as u plus 1, and x plus 7 would be the same thing as u plus 3. Now, the 9 on the other side isn't affected by any of this, so we're just going to leave that a 9. It's at this point that we might be able to take advantage of some clever rearranging when we do the expansion that we thought we were going to have to do anyway. U minus 3 and u plus 3, when we multiply them out, we can take advantage of a particular factoring pattern called the difference of squares. That is, if you multiply these out with box method, FOIL, double distribution, whatever it is that your teacher called it, we're going to get u squared minus 9. For that matter, when we multiply out u minus 1 times u plus 1, those two other factors that we still have left over here, we are also going to get another difference of squares, u squared minus 1. And the advantage here as we multiply out u squared minus 9 times u squared minus 1 is it's just a lot easier to multiply out because we're just doing regular binomial multiplication. My preferred method for expanding stuff like this out is the box method. So I've got u squared minus 9 times u squared minus 1, which is going to give me terms like u to the 4th as I multiply u squared by u squared, minus 1u squared, which we just write as minus u squared usually, minus 9u squared in this lower left-hand corner, and finally plus 9, since a -1 times a -9 is positive 9. As we put all that together, we get u to the 4th minus 10u squared plus 9 equals 9. And that means we're going to be able to take advantage of one last efficiency since that plus 9 on both sides is going to cancel out. Subtracting 9 here, you can see what I mean. We get u to the 4th minus 10u squared equals 0. And that's that 0 we wanted earlier for the zero product property. We can pull out a common u squared on this left side, and it leaves us with u squared minus 10 as the other factor. And just like we did earlier, we can say the only way for this to be true is if u squared itself is equal to 0, which only happens where u is 0, or for u squared minus 10 to be equal to 0, which is only going to happen where u squared is equal to positive 10, which means that this particular u either needs to be the positive square root of 10 or the negative square root of 10. Now, it is important to remember right now that u was our invention. The original problem was in terms of x. So we need to undo our distribution from earlier. If u is equal to x plus 4, we can just as easily say that x is equal to u minus 4. Meaning when u is equal to 0, that's the same thing as saying x is equal to 0 minus 4 equals negative 4. When u is equal to the square root of 10, x is going to be equal to the square root of 10 minus 4. And finally, when u is equal to the negative square root of 10, x is going to be equal to the negative square root of 10 minus 4. And it is exactly these three solutions that we can take back to our original equation. This equation, x plus 1 times x plus 3 times x plus 5 times x plus 7 equals 9, will have solutions at negative 4, which is a double root, by the way. I'm sure some of you know that a quartic equation like this is supposed to have 4 solutions. But remember that negative 4 solution came from where u squared was equal to 0, so we kind of count it twice. X equals root 10 minus 4, and x equals negative root 10 minus 4. Now, back to my skepticism, I could actually not find this in any Harvard entrance exam. When I went Googling it earlier, I saw it on some social media site. But what's interesting is you can find older entrance exams for schools like Harvard and MIT, and there is actually a July 1869 Harvard entrance exam that I have typeset with latex, I don't know why you can't just say latex, and that I have put up on GitHub. So I'll put that link in the description. You can check that out. It definitely has some interesting questions, but the interesting questions are interesting in different ways. These older 19th century entrance exams are usually testing lower level skills that we wouldn't usually expect today's students to do, because today's students, for example, could just take an equation like this and throw it into Desmos. In fact, when we do throw it into Desmos, we can see what we mean by a double root. We can literally see the symmetry in the problem that allows us to do the kind of substitution and simplification that we did earlier. Still though, it is a fun little problem. I hope you liked it. Comment down below if you can find this anywhere on a Harvard entrance exam, and otherwise I'll see y'all next time.